Agents become truly useful and autonomous when they have the ability to take action and produce real world outcomes. Tools allow agents to interact with external systems such as external APIs, functions, workflows to combine models' reasoning with concrete business actions. This introduces a key architectural pattern: the separation of reasoning and execution. Model is responsible for understanding users' intent, planning the steps, decision making, and determining what needs to happen next and in what sequence. The surrounding agent system is responsible for execution by invoking the appropriate tools selected by the model and carrying out those decisions. In practice, this forms a continuous loop where model reasons about the task and selects a tool. The agent system executes that tool and returns the result to the model. The model then observes the outcome and decides the next step. This cycle repeats till the objective is achieved. Model's reasoning defines the plan, and tool execution makes it real. Let us review an example AI agent request flow to understand what happens when an agent uses a tool. The process starts with the user request. For example, what is the weather in Seattle? Before the model generates the answer, it is provided with a list of available tools and their specifications. In this case, the model knows that there is a tool called get_weather, which gets the current weather for the city. It has some input parameters and it returns a specific output. The model first reasons about the request and determines that it cannot answer it from its own knowledge because it needs the current weather information. Therefore, in its output, it generates a structured tool call selecting get_weather function and supplying it with the required argument, which is city is Seattle. The agent runtime then acts as an executor. It takes the tool call generated by the model, invokes the underlying API or function, and passes along this argument. At this stage, the workflow has an option to validate the arguments that are generated by the model and apply guardrails or remediate any mistakes made by the model. Once the tool is invoked, the external system performs the actual work and returns a structured response. In this example, it is the current temperature and weather conditions in Seattle. The result is then sent back to the model, which interprets the data and converts it into the natural language response for the user. The important thing to notice here is that model decides which tool to use and how to use it, and the agent framework handles the execution, creating a clear separation between reasoning and action. This pattern is the foundation of modern AI agent systems. It enables them to safely connect AI reasoning with real world operations. The key reason tool calling works reliably is that the model is given two types of information: the description of the tools and the schemas that it expects and returns. The description provides meaning. It tells the model what the tool does and when should it be used. In this example, the model understands that get_weather is meant to retrieve current weather information for a city. The schema provides structure. It defines exactly what inputs the tool expects, what fields are required, what types are allowed, and even valid values such as Celsius or Fahrenheit in this case. The model uses description to select the tool and the schema to determine how to call the tool correctly. As agents become more capable, they are often given access to many different tools. And the new challenge that they face is deciding which tool to use for a particular use case. The model examines the user's request, compares it against the descriptions of the available tools, and selects the one that best matches the user's intent. In this example, even though the agent has access to weather, flight, calendar, and calculator tools, it recognizes that the user query can be best handled by the weather tool. There are several strategies for tool selection. The simplest approach is model based selection. where the large language model chooses the tool on its own based on user's query and the tool description. Rule-based approaches use deterministic logic written in the code, such as keywords or business values to route the request. Many enterprise systems adopt a hybrid approach where they use rules to narrow down the candidate tool list and let the model make the final choice. In high risk scenarios, the agent can confirm from a human the selection of tool before execution. And as the agent scales, organizations may use dedicated router or classifier models, which are optimized for routing the request to the right tools. The key takeaway here is that tool selection in itself is a reasoning problem. The more tool the agent has, the more important it becomes to implement reliable strategies for choosing the right capability at the right time. And one way to improve agents' reasoning is to organize the tools into meaningful categories. Tools can be grouped by technical function, as you can see on the screen, or even by business domain or business outcome, making it easier for the model to narrow down its choices. In this image, you see categories that are related to technical function. Information tools can help the agent retrieve knowledge from search systems, databases, and knowledge bases. Computation tools perform calculations, analytics, and data processing tasks. Action tools interact with enterprise systems such as Jira, Slack, ServiceNow to drive business processes, and human approval tools introduce human oversight into the loop. In practice, many agentic systems create a hierarchy. They first filter by technical function, such as informational, retrieval, computational, action, or human approval, and then they narrow down the search to relevant business domain, such as sales, finance, or HR. And they finally select the specific business outcome, such as checking the balance or approving an expense or planning a trip. The key idea is that not all tools are equal. By organizing them into categories, we make it easier for the agent to select the right capability. Later in this presentation, we will learn about the idea of skills, which implements this hierarchical organization. We will use skills to filter the tools before sending them to the model for reasoning. Up till this point, tool calling looks straightforward. Give the model a tool, let it generate the call, and then execute it. But in an enterprise environment, the reality is much more complicated. Every integration comes with its own APIs, authentication mechanisms, payload formats, protocols, etc. Whether you're connecting with GitHub, Slack, Jira, or any other system, you end up writing a significant amount of custom integration code. And most of this code has nothing to do with the business logic. And this is the kind of problem Model Context Protocol was designed to solve. Model Context Protocol, or MCP, introduces a standard protocol between AI applications and tools. Instead of every application building its own integration, tools expose their capabilities through MCP servers, and any agent can discover these tools without writing any integration code. Agents use MCP clients for interacting with MCP servers, for automatically discovering the tools that they expose, and then invoking these tools using a standard protocol. The benefits of this approach are that tools can be discovered consistently, integrations become reusable across teams, and onboarding new capabilities becomes much faster. Rather than repeatedly building the same plumbing, organizations can write an MCP server once and connect many different agent systems. You can think of MCP as a universal connector for AI applications and enterprise systems, making the entire ecosystem more portable, scalable, and easier to govern. Besides providing capabilities such as automatic discovery and standardized invocation of tools, MCP also provides access to knowledge and expertise through resources and prompts. Tools, as we discussed, are executable functions. Typically, APIs, functions, workflows all fall under tools. Resources provide access to information such as files, documents, configurations, or records that client can retrieve and use as context. And using prompts, an MCP server can publish approved prompts for different business tasks that follow the organizational standards. Now let us look at the main components of the MCP and how they work together. On the left side is the AI application, and embedded within it is MCP client, which is essentially part of the application and knows how to speak the MCP protocol. Instead of hard coding integration, the client connects with one or more MCP servers using a standard protocol, which is based on JSON RPC. One of the first things the MCP client can ask an MCP server is, what capabilities do you have? The server responds by advertising its tools, resources, and prompts. Once the client knows what's available, it can invoke these capabilities using the same standardized interface. It doesn't matter whether the MCP server is connected to a file system, database, an enterprise application. From client's perspective, the interaction is consistent. It can discover capabilities, invoke them, and consume the results. Basically, the MCP decouples the AI applications from the underlying systems that they use. The MCP server handles the specifics of accessing files, databases, and invoking external APIs. A question that you may have in your mind is, who builds these MCP servers? The answer is anyone who owns or understands the underlying system that the AI application is connecting with. Software vendors can publish official MCP servers for their products. Internal platform teams can build MCP servers that expose enterprise systems such as HR application, data warehouses, or any proprietary workflow. Open source communities are also contributing by building reusable MCP servers for popular tools. Another question that you may have is, where does the MCP server actually run? The answer is that it can either run locally on the same server where the AI application is running, or it can run remotely on the network. The most common pattern that is used today is to run MCP server locally on the same server, however running as a separate process alongside AI application. The AI application contains the MCP client in its process. Client uses the standard input and output or STDIO to connect with the server. What's important to understand is that local MCP server does not mean that MCP server is limited to local resources. It can still access anything it has permission to reach. It basically does the integration with backend systems, and these backend systems could be on the network or even on the same server. For example, it can interact with local file system, execute shell commands, query a database, or work with local Git repository. At the same time, it can also connect with remote systems such as GitHub, Slack, Salesforce, cloud databases, or virtually any web API. When MCP server is hosted remotely on a different server over the network, the MCP client uses transports such as HTTP with server sent events or WebSockets to create a two-way communication with the MCP server. Whenever agents use tools to access external systems, there is an important question to be answered. Whose identity will they use when invoking these tools? MCP itself does not define or require any specific authentication mechanism. MCP is simply a communication protocol. Therefore, MCP servers can use whatever authentication model is appropriate for the environment, including OAuth, OIDC, SSO, API keys, etc. In user-facing applications where agent works on behalf of the end user, the answer is the end user's identity. It can be done using three-legged OAuth or 3LO, where user explicitly signs and grants consent to the application. For example, Alice might allow application to read her email and create the calendar event. The MCP client and server don't create or define these tokens. Instead, they simply use them. In many implementations, MCP server securely stores and manages the user's access token and includes it when calling the external services. As a result, when agent creates a calendar event or reads an email, it is doing so as Alice within the same limits of Alice's granted scopes. The second use case is that agent is used for backend automation, scheduled jobs, or enterprise workflows where there isn't an end user sitting in front of the application to grant the consent. In such cases, a common approach is to use 2LO or two-legged OAuth. Instead of obtaining token through the user's approval, agent maintains a service account and uses that to authenticate its own credentials. The authorization server can issue an access token that represents the server itself. For example, the identity might be something like AI agent production. It can provide permissions for querying the database, updating an ERP system, invoking internal APIs, etc. In practice, most enterprise agents don't operate purely as a user or purely as a service. In fact, they use a hybrid model. There are certain actions that need to happen in user's context because they involve a person's data or permissions. For example, reading the end user's email, accessing Jira tickets, or posting message on their behalf requires 3LO. Other actions that are really system operations, such as running analytics, querying internal databases, generating reports, etc., requires 2LO, where the agent acts as the service principal with its own credentials. The important takeaway here is that agent chooses the right identity for the right task. This hybrid approach gives enterprises the best of the both worlds. One of the promises of MCP is that the tools can be discovered dynamically at runtime. The MCP client connects with each MCP server it knows individually and requests each server's tool list. The MCP servers individually return the tool list, and the client aggregates these tools into a single catalog, which it gives to the model for reasoning. At first, this may seem very reasonable, but as the organizations adopt MCP and the number of servers and tools grow rapidly, this can create its own challenges. The larger tool catalogs can increase prompt size and inference cost for the model. It can slow down decision making, and it can make harder for the model to select the right capability. Similar tools can confuse the model, leading to poor routing decisions and lower selection accuracy. The key point here is that tool discovery does not automatically solve the tool selection problem. The naive discover everything and give it all to the model approach does not scale very well as MCP ecosystems grow. We need smarter strategies. Otherwise, we simply replace the integration complexity with discovery complexity. And one way to solve this problem is to maintain a managed MCP registry where instead of providing every tool to the model, we maintain these tools in a vector database, and at runtime, we do a semantic search to find the most appropriate tools. The MCP servers continuously publish metadata about the capabilities, such as tool names, descriptions, schemas, tags, any examples of using the tools into the vector database. The information is indexed and converted into the embeddings, creating a searchable registry of what each tool does. When the agent receives a request, such as find weather alerts for New York, it first performs a semantic search against the registry and gets a subset of the tools that are relevant for the task. Previously in this presentation, when we were talking about tool calling, we talked about how organizing tools in specific categories can help the model understand their intent, and it can help its reasoning. We can apply the same concept here when we talk about managed MCP registry. We can organize the tools as skills, which are high level capabilities that represent the business outcomes. So rather than exposing dozens of weather APIs, the system can expose skills that align with business outcome, such as get weather, plan trip, check balance. When the request arrives, the agent performs the same semantic search over the vector database, but now it's searching the catalog of skills instead of raw tools. The key advantage here is that we are thinking in terms of business outcomes, which is how the end user also thinks. Organizations can create a centralized, reusable catalog that aligns with the business outcomes and can scale across teams and domains. It can apply centralized governance in this case. Another simpler approach to tool discovery is to implement a rule based discovery where the selection process is deterministic and predictable. The agent first extracts structured signals from the request, like the intent, entity, user role, organizational context, etc., and uses these signals to evaluate the explicit business rules and find the right tools for the task. For example, you can route the sales related requests to analytic tools, customer related tasks to CRM capabilities, and restrict sensitive operations to authorized users. The biggest advantage is transparency. You always know why a tool was selected because the decision traces back to a specific rule. This makes this approach especially valuable in regulated environments where compliance, consistency, and auditability are critical. However, the trade off of this approach is similar to why we have AI systems versus traditional software. The rules do not scale very well as scenarios become more complex and the requests become ambiguous. And that is why many enterprise systems combine both approaches. They first use rules to find the broader categories and then apply semantic search to select the best tools from that smaller pool by applying the metadata filters. And this image brings everything together for tool discovery that we have discussed so far. On the left, you see the naive approach where the MCP client gathers all possible tools from MCP servers and sends them to the large language model. And it has its own problems such as large prompt size, higher cost, slow inference, tool confusion, and poor tool selection accuracy. In contrast, implementing a managed tool discovery using a vector database, skills, and deterministic rules within your workflow is a more scalable approach. It improves the token usage, lowers latency, lowers cost, improves tool selection accuracy, and can scale to hundreds of tools. In the beginning of this presentation, we saw an end-to-end flow of AI agent request flow. This is the same request flow using MCP. The agent first discovers the available tools and their schemas from MCP servers. The MCP client sends the request to the appropriate MCP server, which executes the underlying implementation, rather than the agent system doing that. Model decides what to do. MCP standardizes how capabilities are discovered and invoked. It is important to remember that MCP is an architectural choice. It is not a replacement for tool calling. Under the hood, the agent is still making tool calls. The question is whether you need the complexity of maintaining a standard protocol layer to manage those tools, or you can do well with direct tool calling. The guidance is that you should use direct tool calling when your scenario is simple. If you only have a few tools, tight latency requirements, fixed workflows, and internal integration only, then MCP may not add any value. Rather, it will introduce many unnecessary complexities. You should use MCP when you expect growth and reuse. If you want the tools and data sources to be shared across multiple agents and applications, then MCP can add value by providing a standardized way to expose these tools. If you're building single purpose agents, tool calling is usually enough. If you're building platform of agents that need shared discoverable capabilities at scale, then MCP becomes a strong fit.